So that's the interesting thing about, or the difficult thing about space. And for the business, you can build and test as well as you want on the ground, but you can only really test it once it's launched. If it doesn't work, it didn't work, it's dead. You can't do another iteration, you can't fix it, you can't improve on it.
Mike, why do you do the work that you do?
Didn't expect that as a first question.
Welcome.
Completely honest, I'm not one of those people that's had a specific passion for a specific thing and then started chasing it, type of thing, right? I'm an engineer. I studied engineering, and I've got a need to create something, right? I really struggle to sit still at home ever. So, I always want to be creating something, creating value, building something, designing something. I mean, I get up and I go to work and I enjoy my work purely because of that. Doing the engineering work, doing the management work, running the company, solving problems, figuring things out, creating value, really. But I'm not one of those people that was originally super passionate about space and then went into space, to be honest. I studied and then did my master's, and there was opportunity for my master's in the direction of space. So originally I thought I wanted to do something in the medical field because I mean, that's the most complex and interesting machine on Earth is the human body, right? So that really fascinated me, and that's what I really wanted to do originally. But I couldn't quite find a master's that was interesting and relevant at Stellenbosch at that time. And then there was the opportunity to do something in space. And I ended up doing my master's in control systems in space. And towards the end of my studies, there was a mission idea contest in Japan where the students, me and some of the other students at the university, we entered. We came up with this very cool idea for a satellite constellation that gives internet to other satellites, and we call it the outer net instead of the internet. And we won. So I went to Japan, we pitched there, and we won the competition. And we used that money to buy a coffee machine for the office.
So you didn't build the outer net?
No, but someone else did.
Oh.
We recently found out, like, there's a company, I can't remember, someone in Europe that's building the outer net now. It's called the outer net. It's the same thing. That's super fishy. Anyway, so we continued, and then there was a whole lot of research done at the university at that time, led by Professor Stein, all focusing on control systems. So my masters and a whole lot of different masters kind of played into that. And at that time, there was an opportunity for us to build control systems for a satellite constellation in partnership with a university in UK that Professor Stein also had a relationship with. And the university was contracted to build those things. Me and some of the other students there then took a whole lot of the research that was done at the university and then turned it into products under guidance of Professor Stein. And we just winged it.
The university was contracted to produce satellites in...
Control systems for satellites.
Control systems for satellites within the research group.
Yes. And
then in that contract, you were able to maintain the ownership of the designs and IP of that while you just deliver the control system.
Yes.
Okay.
So basically there was a constellation of satellites called QB50, something funded by the European Commission and like some EU funding through an institute called the Von Karman Institute for Fluid Dynamics in Belgium. So what they did, they wanted to do research on the atmosphere of the Earth. So they wanted to get these specific sensors in around the Earth with many different satellites, starting at a certain orbit and then slowly going down, falling back to the Earth, and then measuring characterizing the atmosphere. But to build 50 satellites would be expensive. So what they did was they built 50 sensors. They then put a call out to say, if you build a satellite and you house our sensor in your satellite, we'll give you a launch. So they got a launch for 50 satellites, and they built 50 sensors, and then they got international universities and small companies to build the satellites. So sharing the costs, it's a win-win. But a lot of those satellites were built by universities, and they had no idea how to build satellites. And the control systems are the most complex part of a satellite.
And if you could just give us a layman's definition of control systems.
Sure.
An application.
Okay. So a control system is effectively the system that measures where a satellite is pointing and then rotates at the point where you want it to point. So, you'll have on your satellite a camera that you want to point to a specific target on Earth. The satellite's just floating in space, right? You need to turn it to point where you want it to point. Or you have an antenna on your satellite that you want to point to your ground station, or whatever you want to do. Or point it to a star in deep space, or whatever. So to do that, a car on Earth has wheels that's in contact with the road and that can steer you, and you can use the Earth's magnetic field, your compass, or look at landmarks or whatever and navigate with that. In space, you can look at where the sun is relative to yourself. That gives you a direction to the sun. You can look at where the Earth is relative to your satellite, so how the satellite is rotated relative to Earth. You can measure the Earth's magnetic field, and you know what that magnetic field should look like. It's a dipole. And you're moving through that magnetic field. You know where you are in your orbit through using GPS or a mathematical model. So you know what the magnetic field should look like. You measure it, and then you compare those two, and then you can get an idea of how you rotated relative to the Earth's magnetic field and then relative to the Earth. And then you can look at the stars. So you basically take an image of the stars with a very sensitive camera. You find all the dots, you look at that pattern, and you compare it to a map that you have on board of all the different patterns in all directions. If you've got this catalog, and you look at that pattern that you're seeing, and you find where in the catalog you're looking at, and then you know where you're actually aiming. So that's the most accurate way of determining your orientation. So a combination of the sun, Earth, magnetic field, and stars, you estimate your orientation. Now you know where you're pointing. You know where you want to be pointing. You need to turn there. So to turn there, you use one of two ways. You either generate your own magnetic field. So if you have two magnets, they interact and push each other. They've got a force or a torque on each other. So you've got the Earth's magnetic field. You generate your own little magnetic field, and you've got three little magnet torquers that can generate a magnetic field. And that interaction then turns the satellite. So you measure the magnetic field, you generate your own, and then that turns the satellite. That's the one way. Other way is with reaction wheels. So you've got little electrical motors with heavy disks. You spin the one in the one direction, the satellite spins in the other direction. So like a Newton's third law type of thing.
In terms of education, so I want to go back once more.
Yeah.
You studied E&E.
Yeah.
And then you did your master's in E&E.
Yeah.
And while doing that, you also did quantum mechanics online at University of Berkeley.
Yeah.
So is that where the education and seeds were planted for you to pursue this field?
I did my master's in E&E, and my master's topic was in space, and that's where I got the exposure and learned what I learned. So I did the E&E undergrad, then E&E postgrad, and I did that quantum mechanics course, and then we started the company. But in the beginning, I wasn't really sure what it was going to be, and I thought what really intrigues me is system engineering. So instead of just focusing on one field, to rather look at the system and have an understanding of all the different parts of the system. So I then did a master's in mechanical engineering part-time. So I studied at Stellenbosch University, did a master's, but it was part-time while I was working. And it was in mechanical, and I didn't have mechanical undergrad. So, in my master's, I needed to do advanced heat transfer that built on 5 undergrad heat transfer courses that I didn't do because I didn't do mechanical engineering. So that was super tough. So I had to do a lot of research in my own time and figure things out and that kind of stuff. But yeah, that gave me a good overview of both the mechanical and the electronic side.
So with what you were originally saying, you wanted to do something medical, and then because the human body is so complex, you couldn't find an interesting enough masters to chase that. But it almost sounds like, as you were unpacking, even thinking myself, as you're talking about star maps and magnetic fields, it's not something you can go and observe.
Yeah.
You need to pay millions of dollars to go and observe these things. So it's so ambiguous. It's a very interesting problem set to go and try to solve.
And I mean, those early days when I was doing my master's, and then that satellite competition we did in Japan and stuff, as soon as you start working with space stuff, it starts it bites you, right? Because you start thinking about
sci-fi,
the concept of floating in space, and you start really going into the details of all of these sensors and things, and you get your first image from space. Our sun sensor is a small little camera, right? It's the type of camera you use in your reverse cams on cars and stuff that we just modify a bit and stuff, but with specific filters and algorithms and stuff on it. Now,
so an iPhone camera is more sophisticated than what you're using to drive satellites.
For sure, yeah. You can program an iPhone camera to be a very good sensor on a satellite, actually. But the thing is, electronics they break in space because of radiation. So you put an iPhone up there and it'll break very quickly. With that camera for the sun sensor, for instance, when we launched the first one, so we designed it and we tested it as well as we can on Earth by making like a sun source, a light. And testing it outside and whatever, but you have to fly it to really test it. So that's the interesting thing or the difficult thing about space. And for the business, it's kind of the barrier to entry for new companies, but it's your moat once you're an established company is you can build and test as well as you want on the ground, but you can only really test it once it's launched. If it doesn't work, it didn't work. It's dead. You can't do another iteration. You can't fix it. You can't improve on it. So it's very difficult to do R&D in space because if you're building something on the ground, you can build it, you can test it, you can learn, you can go through that. I love that the build, measure, learn, lean startup kind of thing. It's very applicable here because to build these things are very complex. It's expensive. It's expensive to launch them or whatever. The measure bit, if a satellite fails, you can't communicate with it anymore. So if something breaks, you don't learn anything, right? You don't get feedback. You don't learn a lesson or see what failed. If it fails, it's gone. So the measure bit is very difficult. And obviously then the learn part, the interesting thing there is, even if you learn that something isn't good in your system or something failed in your system, if you change anything, it actually makes your product less desirable to customers. Because customers in the space industry want something that's already flown and that's already been proven. They don't want new stuff. They rather take something with a bug that's known than something where you fix the bug. So long to build, impossible to measure, and then even if you learn something, you can't apply it because then people don't want it. So that's why the R&D cycle is just so slow.
There's a market resistance to learning and implementing new
Exactly.
How do you mitigate that?
You partner. So we have very specific customers that we've built partnerships with that are very innovative and pushing the boundaries, and they want the new stuff. They're willing to take the risk of flying something new to be able to be better than everyone else. I just want to wrap that, go full circle, just conclude what I want to say about that camera is, it's a sun sensor, and we've tested it as much as we can on the ground. We launch it, we test it up there, we get the first images from that thing. And you get a very low-res fisheye image with the Earth there, where you kind of see a continent, but it's from a little camera that you built.
Wow.
Yeah.
And at that point, I made a little post on Facebook or LinkedIn or whatever with this really crappy low-res image and freaking no one else cared about it because it's a terrible image. But to me, it was so valuable. Now looking back at it, I'm like, oh, that was cute, because now we're building control systems for satellites that's taking amazing images.
Yeah.
But just that thing of getting something in space and seeing an image or data that from the thing that is in space is so incredibly rewarding, and that's why it completely hooks people, the space industry.
And going into your current, call it products and service offering, could you walk us through a brief overview of your different types of products that you offer to your clients?
Yeah, so we do, as I said, the sensors. So a sun sensor, earth sensor, magnetometer, star tracker, and then the actuator. So magnet torque rods and reaction wheels. So the stuff to measure where the satellite's pointing and the stuff to turn the satellite. So we sell those parts to people that have the skills and ability to build their own control systems. So they take a computer space computer that interfaces with the sensors, gets all the sensor data, then does complex like mathematical calculations and models, and then calculates the command to the actuators to turn the satellite, and then they make the full control system. That's a part of our customers. There are a few people with that skill. Like that's a specialist field, the control system field. What we do is we also have our own computer, our own space computer, and we take that computer with a collection of sensors and actuators and then give a customer like a turnkey control system. So they just plug that thing into their satellite. Their satellite's main computer tells our system, I want to point to Cape Town Stadium. And then we do all the calculations and do all the control. So that full control system is really our core business. There are very few people in the world that do that. And it's becoming more and more relevant and important as more and more startups and young companies start building satellites. I mean, in the old days, it was the Americans and Russians racing to get to the moon.
Did that really happen?
Of course. So, it was governments building satellites, and it was really big satellites. Now, with privatization and commercialization of the space industry, driven by, Elon Musk making launches a lot cheaper with reusable rockets and stuff, the space industry has been commercialized. It's called the new space industry now. That's when they refer to new space. And it's basically the idea of building satellites cheaper, quicker, launching them faster, building them with commercial electronics. So, automotive grade electronics that you find the good ones and you launch those ones instead of using radiation hardened electronics that NASA spent, tens of years to develop. You build it with cheap electronics. And the interesting thing is they last almost just as long. Not quite, but I mean, it's been incredible how well these satellites last with just commercial electronics, if you find the right ones.
Imagine if Radio Shack still existed and we could go and build satellites at Radio Shack. Amazing. You have a retail market, direct to consumer for your components.
Yeah.
You just gave Mike an idea.
You alluded to in part of the build, measure, learn. It's easy to build, easy.
Yeah.
You can solder things and put stuff together. But then to measure it, if anything goes wrong, it's really hard to communicate and make something happen. Do you have a specific experience of one of the projects where it launched and you couldn't communicate with it, or it was really hard to? It's man, the schlep of that. Maybe it's a loaded question.
I don't even know if I want to open this box.
I remember a week or more of nearly sleepless nights. You have a kid now, 4 or 5 weeks old. Worse than that even, I think, your sleepless nights trying to...
Yeah, so I mean, part of the QB50 project of these 50 satellites, we also built one of the satellites called Zeta Aerosat. And where we built the control system, but we also built the entire satellite. So we bought certain components in, and we built the satellite, and wrote the software and stuff. And so, yeah, I mean, end-to-end systems engineering, putting the thing together. I mean, we're talking days before needing to ship, sitting in the clean room, pulling all-nighters, but it was just get it done type of thing. It was very cowboy wing it, just make it happen type of thing. And we built an incredible satellite in the end. Anyway, flew to Netherlands to go deliver the satellite. Flew with a satellite in my hand luggage, literally.
Like a Jason Bourne on an airplane kind of
through the little scanner. I'm just what? What are they going to do? And you know what the crazy thing is? I set my bag through there with a laptop in. They stop you and they search you. You put a satellite through a scanner at an airport, no one even blinks. So I went all the way through Dubai, through everywhere with the satellite, no one noticed.
Oh my goodness.
Anyway, delivered the satellite, and then it was launched. And then once the satellite's launched, it's launched in a cluster. Right, so there's all of these satellites up there, and then what they need to do is they need to deploy the solar panels so that they can start generating sun, or you don't have to in the beginning. And then it needs to deploy their antennas, and then once the antennas are deployed, it starts just beeping, sending out a little a beacon. and then you listen on the ground for that beacon. And once you've received that beacon, you can start like tracking the satellite better, and then you can tell it, okay, switch on this bit and this bit. And you slowly start switching the satellite on. You don't want it to autonomously just go do things and then maybe drain its power. It might be floating in a way where the solar panels are not pointing towards the sun. Now you switch everything on and it drains the battery all the way and it doesn't ever switch on again. So you need to slowly commission the satellite. Now, in the beginning, there's 50 satellites sending out a beacon. So all of those signals are coming in all mushed and scrambled and whatever, so you can't really, so you wait a while and slowly the satellites drift apart. And then you've got better like separation between the satellites, and you start pointing your antenna towards where you know the satellite should be. And then you start listening, and you listen for your beacon on your frequency, because each satellite has its own frequency that's allocated to that satellite. So you listen on your frequency, and you then slowly wait until it's clear and there's no other satellites muddling it up. So that first bit is you wait. You know, satellite launch, you point your antenna, you wait for this, so the satellite comes over your ground station twice a day. And it can be it can be in the middle of the night or wherever, but you know, when it comes over your satellite, you need to wait for it. And you're just like literally sitting, waiting at that screen, waiting for a little blip. And like big event, everyone's waiting and nothing. Yeah, you don't see anything. And then we wait and we don't see anything. We get people together and it's like super exciting, and then everyone goes home like, oh. And then, you know, wait for the next overpass. And we're thinking, okay, maybe it was just pointing the other way, or the battery's just flat or whatever. And nothing. You just wait and you don't hear from the satellite. And, you know, then at some point we saw this very tiny little blip, but very weak signal. And we were super excited because it was something. And, you know, it was a long process, and we keep seeing these tiny blips, and then we started figuring, okay, you know, something's going on. It's alive, but something's going on. So we started communicating with it as if it's alive and telling it to do things. So the most obvious conclusion was that the antennas didn't deploy. So it's got these big deployable antennas. If the antennas are not deployed, it doesn't have a good like directional antenna. So it's sending out a signal, but it's uniform, like omnidirectional, and you get a very small little signal on the ground. So
it's getting power, but it wasn't.
The satellite was on,
yeah,
and it was trying to communicate, but we couldn't hear it because the antennas were not deployed. So Professor Stein and I upgraded the antennas on the roof of the engineering building. I've got pictures. It was literally the one day, it was like gale force winds and raining. And he's the professor. I'm a student there. I was literally on like hanging on the poles with this massive wind, like hanging these big antennas and upgrading the filters and amplifiers and stuff. And we've just put these massive antennas on our roof. Say like, if those antennas are really crappy, let's put huge ones on the ground.
Yeah.
And we upgraded the amplifier to be very large. And we just made our ears very big, and we started shouting very hard. And then the satellite could hear us. So it responded to our request, but with a very faint. It's now a little bigger because our antennas were better. But in the end, the antennas didn't deploy. So it was there, it was working, but we couldn't get like data from it, so we couldn't use it the way we wanted to. So it was an incredible learning experience. It was sleepless nights and very innovative stuff. But in the end, it was, you know, it's a failure.
Failure. I mean, that particular mission might be chalked up as failure, but all the lessons and also the team bonding with you and Jaco, Christu, Prof. Stein. It's like you're on the roof with your professor, putting antennas together, aiming at trying to troubleshoot this thing. Like, what a great adventure! That brings you guys together.
And I mean, it's a failure from the point of view of operating the payload of the satellite.
Yeah.
But it's a massive success in terms of learning how to commission a satellite, building the team, learning what would be the things that our customers go through. The guys that are building satellites, that put us in their shoes. We understood a lot better what they go through when they commission a satellite, which gave us a lot of insight into what are the things we need to focus on when building our own components to make it easy for them. I think it very nicely ties up to the concept of like understanding your customer. There's no use building something that you think is great. You need to build something that actually solves their need. That whole experience gave us very, very good insight into what they actually experience and what they need.
And the things they might not tell you. It's the things that it's more nuanced, and it's, I need a control system, but you don't know I need a control system with this and this and this and this.
Absolutely.
Outside of just the system.
And it's easy to design something for when things go right, but it's when things go wrong where the good designs work. And they it's difficult for them to tell you what they need when things go wrong, but experiencing it firsthand really gave us a lot of insight. And I think to a large extent that made us really be successful in the beginning, because all of these teams starting out, building their first satellites, we could tell them, we just built our first satellite. We learned a whole lot of stuff. We really helped solve their problem. And that's why we also, just selling the parts is less interesting to me. It's selling those complete control systems to customers. That's where it's interesting, because they come to us, our typical customer comes to us saying, I want to build a satellite this size. This is what it needs to do. I've got no idea. And then we simulate for them. We write them a report. We give them a proposal all for free. And then they tell us, okay, I want the thing. And then we put something together for them. But the whole mindset is helping them solve their problem, get their satellite in space to do the thing that they want to do.
How are you able to expand your customer base?
So in the space industry, the main marketing outlet is conferences. So space satellite conferences. So when you buy a control system for your satellite, it's not like you're going to go on Amazon and pay with your credit card. You need to actually speak to the people first. It's a trust thing, because if any one part of your satellite fails, the whole satellite fails. So in this satellite industry, trust and reputation and reliability is the single most important thing. So it's showing them data of your things have worked. It's convincing them to trust you and that kind of stuff. So early days, the first conference I went to, still as a student at that time, to one of these QB50 days, one of the conferences. And then some of the more established companies, they're at booths where, they've got their backdrop and they've got their salespeople and their components and their brochures and whatever. I still went to that at that point, just brochures I designed in Microsoft Word. I had a website that I built in my free time. On like Wix or one of those free things, and I always joke it was that creepy guy at the lunch table with the opening my jacket, selling my satellite components type of thing. But I was literally sitting at the lunch table. Prof. Stein was also going to these. We were going there and at the lunch table speaking to people, finding out if they're building a satellite. Do you have a control system? Oh, we have these things, and then giving them these really cheap brochures and pointing them to the satellite. And people, the need was so big at that point that even though our marketing was crap and we didn't have a lot of experience, people were going, well, we need something and you have it, like what's your price? And at that point we were just going way cheaper than anyone else. And these guys had small budgets because they're just starting out. So we gave them something that had less reliability and heritage than some of the established guys, but it was way cheaper. And we make the sale, and the sale was building the connection with the person, making them feel like you understand them, and this whole building the satellite was a big part of that. Being able to connect with them, relate with them, build a relationship with them, and then say like, we've learned a whole lot of stuff, and yes, we don't have a lot of heritage at that point, but then convincing them with your technical knowledge and making the sale. And making the sale is convincing the other person that what you're going to sell them is going to solve their problem. And that's
maybe chasing a little bit there. So there's probably two sides to a question. One, how important was timing in Cubespace success? Because timing can be a factor, but you also need to be the right people and team and have the right product to take advantage of the timing. And then maybe the other side of it too, like talking about space heritage, and you were a group of kids and with the professor, How important was the university backing from Sunsat way back in the 90s as almost like a proxy of space heritage and credibility that created that timing for you to be able to take advantage of that? Maybe split that into two questions. But
the technology or the research that was done at that time, and the know-how that was developed, and the kind of space heritage that was developed here, the antenna that's on the roof, that we used for commissioning Zeta Aerosat, all of those things needed to be there for us to be able to do what we did. So there's a massive amount of history at the university that if it wasn't there, there was no way we could do what we did. No way. There was a whole lot of research done at the university. That, the knowledge that Professor Stein has and the experience that he has, I mean, if he didn't do all those master's research and trained all of us, and then
decades before you,
and then if we didn't get that contract with the other university for those initial stuff, none of it would have happened. So there's massive amount of context that made this possible.
Yeah.
And then in terms of timing, as I said, it was just when CubeSat started picking up, the small satellites started picking up. There was a massive amount of new people building satellites. There weren't many suppliers of full control systems. There were suppliers of the parts, but no one solving the entire problem. You still needed the control system expertise in-house to be able to build your own system. But I think the thing that made it possible at that point is making the sale. It was hard work and a lot of traveling. But, I needed to turn into a salesperson from an engineer. And that was a process, a massive process. I mean, my skill now isn't engineering anymore. My skill is making a sale. And my skill is, understanding business. My skill is motivating people and building a culture and hiring the right people and putting the right processes in place and that kind of stuff. It's not engineering anymore. But at that point, it was learning how to be a salesperson. That was going to conferences, speaking to people, seeing their response, realizing what works and what doesn't work, learning how to listen to what the person wants instead of telling them what you want to sell them. And many, I mean, the first phase of our company was me coming back from conferences and Do and Jaco and Christo and Professor Stein at home waiting for me to come back and then make unreasonable demands. So basically every time I come back from a conference, I would say, I sold X, and it was something we don't have yet, type of thing. And then they needed to make it happen, and like they hated me for it. But I wasn't selling what we had. I was selling what the customer needed, and I needed to use my judgment to say, how far is that from what we have, and is it reasonable for us to be able to make it? And then if you ask the engineers at that point, can we do it? They would always say no, because there would be risk involved. You wouldn't be sure it's going to work. It would be complex, and but there's a balance. You need to take risk in business, right? And the risk is committing to these things that you're 80% there, and the 20% is uncertain, and being able to make the judgment call of whether you can do it or not, and then getting the timeline right, and then getting the price right. The price in terms that you can still make money, and also the price in terms of what they're willing to pay. So that was a big juggling act of going out there, finding out what the need really is, then making commitments and promises and solving the problems, and then convincing the guys at home to actually buy into it and build it. Because, I mean, who am I to tell them we are going to build it? I mean, I'm not their boss. It's my peers, right? Shareholders with me, and it's my peers, and it's the professor, that was my professor. But I needed to convince them to follow my lead in terms of what we need to do. So that persuasion of your own team, the persuasion of your engineering team and your professor and that kind of stuff, that's also sales, right? It's also selling to them that this is what we need to do. And